Good morning, students. Welcome you all for physics session. Well, students, in last class we discussed about electric potential, potential energy, and the concepts which are related with electric potential. Done. And we have started the discussion on capacitor, capacitance of a capacitor. In last class, we just discussed about capacitor, definition of capacitor, SI unit, and along with that, how exactly the capacitance is going to be measured. The capacitance of a capacitor can be calculated. Okay, these all facts were studied. Now, move on to, in today's session, we will go for the further continuation of the part, that is capacitor combinations. Yes, in last class we discussed about the fact is that about capacitor. Capacitor is a energy storage device, right? Now, so we have the potential, we'll apply some potential for an electrical circuit and we'll get some capacity in it, and there how one can use the capacitor, how one can increase the capacity of a capacitor, how one can decrease the capacity of a capacitor. These all questions are existed, right? For these questions we have the answer is combination. Yes, combinations of what? Combinations of capacitor. Okay, so using the combination of capacitor, we can increase the capacity and we can decrease the capacity of a capacitor of energy. Okay, now, so how many combinations we have? We have two combinations. These are series combination and parallel combination. So these are the two combinations where most of all electrical circuits are consisting. Okay, so series combination has its own significance, parallel combination has its own significance. Okay, so we'll discuss first of all meaning of series combination and parallel combination. Along with that, we'll discuss how one can construct series combination of capacitor and parallel combination of capacitor, and later on we'll go for the further derivation on series and parallel combinations. Okay, now, so series, this word is very common for you people, right? Everyone is fond of cricket in India especially, right? So we might have heard about 5 test series are there, 5 ODI series are there, 2 T20 series are there, right? So in all these we are using the word series. So what do you mean by series then? Series indicates which is not a discontinuous, nothing but which is continuous. So one by another, by another, by another. If it goes in a sequential order, so that is nothing but a series. Then what is the meaning of parallel? Parallel is a thing which will come or which will go along with some other thing. Nothing but it requires something. Okay, so this is parallel. So parallel in words we are saying that it is making with a junction. We'll form a junction, we'll take 2 or 3 forms of junctions, later we'll go for the parallel. Okay, now how exactly the construction of series and parallel is going to happen, I will show you. First of all, I want to discuss series. Okay, so we'll have 2 capacitors. So series combinations are there, no? So combination is there. So because of that, at least we require 2 capacitors. Okay, and at the same time, you may have n number of capacitors also. So this is a symbol of capacitor. 2 parallel plate capacitors are taken here, and these 2 parallel plate capacitors I have connected with the cell. Current has to pass through, right? So this is the symbol of cell, where the longer edge or longer line indicating the positive terminal, whereas the smaller one, taller, shorter one indicating the negative terminal. And as you know, current will start in the positive terminal, so this arrow mark is very necessary to show current flow direction. So this is capacitor 1 C1, this is capacitor C2. So where we have a parallel capacitors, such that here we have plus Q charges, here we have minus Q charges. So for that sake, we will call it as C1 and C2. Okay, now so such diagrammatic representation or electrical circuit for a series combination of capacitor. So these arrow marks are indicating the flow of direction of current. Okay, move on. It starts with the positive terminal and ends with the negative terminal. Okay, move on. So series combination shortly called as end-to-end connection. How the exactly connection is going to make, I will tell you. See, here we have the C1 and C2. So if a series combination is said to be series if the second parallel plate of a C1 or the negative terminal of a negative plate of a C1 is connected to positive plate of the C2 and the negative plate of the C2 is connected to positive plate of the C3. Select one, go on when you are connecting n number of series of combinations of capacitor. Such a combination is said to be series combination. Now, the thing is to understand in this combination is to about the potential. How potential is distributed and how charge Q is distributed. Okay, now it is clear that in series combination and in parallel combination, potential and charge is not going to be similar. Is not going to be similar, is not going to same because though they are differentiated as series and parallel combination, right? Now, so current is started down, charges are going to move. The charge Q has to pass through C1. The same charge has to pass through C2 because they are connected end to end. There is no discontinuation here. So because of that, what happens here? C1 will have a different potential of V1, whereas C2 will have a different potential. So V1 and V2 are the different potential for C1 and C2. If you connect C3, C4, C5 up to Cn, we'll have to write V1, V2, V3, V4, so on up to Vn. Okay. Now, but charge Q is same. Charge Q is a unity. Now, how to calculate total potential then? So total potential V is equal to V1 plus V2. Isn't it? Now, so let us recall a vice captain here. What do you mean by vice captain? Q is equal to V into C. Vice captain formula have to keep throughout the capacitor concept. So V is equal to V1 plus V2. So how I can write V is equal to? V is equal to, we can write Q by C. We write the same thing. Q by C plus Q by C. Students, notice the point. There I used the term V1 and V2, but in second format I did not use anywhere 1 and 2. Now, I left at this thing, we need to understand through circuit. So, here what they said now, few minutes back, I just said that Q charge is the same which is passing through C1 and C2. So, there will be not a question existed that where I am supposed to write 1 and where I am supposed to write 2. The thing existed is that C1 is there, C2 is there. I have taken here two capacitors, right? So C1 and C2 must be written here, isn't it? So what is the thing we need to notice here? Q charge is a constant. Take outside. What left here? 1 by C1 plus 1 by C2, right? Now, so V is equal to Q into bracket 1 by C1 plus 1 by C2 is there, and move on to V is equal to, I'll just modify the terms here so that I can get my equation. So just shift the charge Q to LHS and the thing left is 1 by C1 plus 1 by C2. After all, what do you mean by V by Q? Remember the vice captain formula, V by Q. What do you mean by V by Q? V by Q is nothing but C. So 1 by C is equal to 1 by C1 plus 1 by C2. So here the thing is to understand. So this is the total amount of capacitance of this two series combination of capacitor. So what do you mean by C then? It is the equivalent capacitance. This is the equivalent capacitance. So because of that we will write 1 by CS. What do you mean by CS then? Capacitance in series combination. Okay. So 1 by CS is equal to 1 by C1 plus 1 by C2. If n number of capacitors are connected, then we need to write the formula 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on up to plus 1 by Cn. So this is the equivalent capacitance of a capacitor when they are connected in series combination. Okay, so move on to further thing. We'll go for the next combination. That is, well, students, few minutes back we just completed the series combination of capacitor. Right? Now we'll go for the second combination, that is parallel. In discussing the parallel combination, what did I say? I just said that parallel combination is such that where would we look for a junction? Nothing but number of charges or number of electrical waves are connecting a point at a common terminal, and there it will start at the rotating. So the combination electrical circuit will be in this one. Here also we are taking the parallel plate capacitors. So this is how the parallel combination is going to construct. Right? So these are two capacitors C1 and C2, where they are connected to battery. Plus and minus terminals are there. Current will start from here and it will goes here. But here what happens? Current will distribute in two region. Charge Q has to distribute to C1 and C2, and then it has to pass through C1 and C2, and then they have to move to a common terminal or a common junction. So in this way, in a parallel combination, charges are going to distribute. But the thing is to notice here, whatever amount of charge was sent through or sent from the battery, those charges will not move in the same proportion, but they will move in a C1 and C2 proportion. Okay, now move on to, so how to calculate the charge and what about the potential? Though they are connected in a junction format, potential will be same. Okay, so charge is going to different. Charge Q is equal to Q1 plus Q2 is that. Because here charge Q1 will move, here charge Q2 will move, because C1 and C2 has to pass through. Right? Move on to Q1 and Q2 is there. Let us recall the wise captain here. Q is equal to V into C. So what do you mean by Q1? V into C plus V into C. Once again, we have the same criteria to follow. Now, where you have to write 1 and 2, write 1 and 2. What did I say now? Charge Q is differentiating, right? Q1 and Q2. So, what about the potential? Potential is same. So, I need to write here C1 and C2. We need now to write V1 and V2 here, because potential is constant. The same potential has to pass through. Whatever the amount of potential at C1 is there, the same amount of potential has to be at C2. Now move on to V is common. So C1 plus C2 left hand here. So Q divided by V equals to C1 plus C2. So what do you mean by Q by V? Q by V indicates what? Indicates C. So C is equal to C1 plus C2. So this will be the parallel combination formula. So what do you mean by C? C is CP is a total amount of capacitance in parallel combination. So Cp is equal to, what is the formula? C1 plus C2. Okay. Now, if n number of capacitors are connected, C1 plus C2 plus C3 plus so on up to Cn, this is the formula we need to remember. Now, one thing we need to notice at the electrical circuit diagram is, here I have drawn electrical circuit for two capacitors when they are connected in parallel. But at the end, we got the equivalent capacitance in parallel combination, right? But here I did not show what is the equivalent electrical circuit. So while deriving this derivation, we should remember to draw the equivalent capacitance in a parallel or a series combination. Both we need to remember. Now, how to write the or how to draw the electrical circuit for equivalent capacitance in series and parallel combination? So what happens here? C1 and C2 are going to add up. They are going to sum. They will mix up. So nothing but C1 and C2 will merge into Cp. The meaning is very simple. No? The meaning of this expression is quite simple. Is that Cp is equal to, we have written here C1 plus C2 plus C3, C4 up to Cn. So nothing but the C1 capacitance, C2 capacitance we have added up. And this amount will be equals to Cp. The meaning is quite simple. The same thing has to apply here. So what we need to do? We need to get only one capacitor with the battery. Plus and minus terminals are there. So this will become the C, where we have the plus 2 charges at one plate, minus 2 charges at another plate. We need to show the direction of current also. So C1 and C2 will combine into a CP format, and that is the combination. If suppose we have a series combination, we need to write here series. That's it. Okay, move on to, well, students, few minutes back we are discussing about capacitor, and we are at the end portion of the second chapter and end portion of the capacitor or capacitance concept. Okay, now, so what is that? Energy stored in capacitor. What is the amount of energy can be stored in a capacitor? What is the amount of charge you need to substitute? What is the amount of potential you are supplying to the circuit? So depending on charge and the potential, how one can distribute the, or how one can imagine what is the amount of energy stored in a capacitor. So for that we need to go for a derivation that is called energy stored in a capacitor. What I have taken here, I have just taken a capacitor which is connected with the battery. If I want to transmit the plus Q charge plate to the minus Q charge plate, what I am supposed to do? I need to apply the more and more amount of force. Why? Because if I want to take the positive charge from negative plate, here I have to came across with the force of attraction. If I want to substitute or induce the plus Q charge to the plus Q charge plate, I need to fight against the force of repulsion. Isn't it? So force of attraction is there, force of repulsion is there. So in this particular case, what I am supposed to do? I need to work on it. There should be some amount of work has to done. Correct? Now, so before that, we need to understand what is the amount of potential is there. So my reference I will take it as V dash. So what do you mean by V dash then? So V dash is nothing but charge Q. So let us take small q, Q by C. So W dash is equal to Q divided by C. This is just nothing but a vice captain formula. Q is equal to V into C is there, no? So for my reference, I have taken it as V dash instead of V. Why I have taken V dash? Will declare at the end of the derivation. Okay, now move on. So V dash is equal to Q by C is there. Call it as equation 1. Now, so what did I say? I just said that we need to work on it, right? So what is that amount of work? I will take first of all the small work then. dW is equal to what I am supposed to do here. I am supposed to do V into or V dash into dQ. Just define the charge definition. What do you mean by charge? Charge is an amount of work done. Amount of work done in bringing the unit positive charge. That is called as electric potential. Well, here we are taking the energy. Energy is stored in the form of work done now. So dW is equal to V dash into dQ. So substitute the V dash value Q divided by C into dQ. So what is this? This will be your small amount of work done. Now, what I am interested in to calculate actually, so I need to or I want to calculate what is the total amount of work done so that I can get energy stored in a capacitor. Right? Now move on. So W is equal to, so there I have differentiated the term. So what I need to do here? I have to integrate the dW, small amount of work done. Actually what you are doing? You are doing the work against the forces, right? So initially it has a charge 0 and you are adding it to become plus. Okay? Now, so integrating 0 to Q. What do you mean by dW? dW Q by C into dQ. So I am integrating the terms. What is the condition I have to follow? Constant terms we need to take outside. In this expression, what is the constant term? Constant term is 1 by C, 0 to Q. So Q left hand, Q into dQ. You may ask me, so why C is a constant term? It's a C, it have a letter C, so it's a constant. No, that is not a thing. C capacitance will be constant for a fixed capacitor. Keep remember this one. Okay, so 1 by C integral of Q into dQ from 0 to Q. Okay, now 1 by C. Anyhow, in first year we have studied the gravitation chapter, thermodynamics chapter. In that we have integrated and as well as differentiated the few terms. Okay, now first of all I want to clear x raised to n into dx. The integration of x raised to n into dx will be x raised to n plus 1 whole divided by n plus 1 c. This is the integration formula. And you may ask me, so where have I done that? Because here I have a term which is very similar to this form. Isn't it or not? Check it out. Keep outside the 1 by c and just look at the integrate of q into dq from 0 to q. Isn't it have the same thing, no? Right? So just apply the things. What do you mean by x raised to n? Here in the place of x I have q. In the place of n I have 1. In the place of dx I have dq. Just integrate it. So what is the formula? X raised to n plus 1. Nothing but q raised to n plus 1. I mean to say nothing is there means there will be 1. So 1 plus 1 2 divided by n plus 1 2 into d. dq, integration of dq will be 1. So where to where? 0 to q. Plus c is there, that is integration constant. And later on when you are moving with the terms by terms or step by step, the integration constant will have a very negligible value, so we'll ignore plus. There is no problem with that. Okay, now move on to what left it here, 1 by c. So we need to apply the upper range and lower range. In the place of small q, you have to apply capital Q, minus in the place of small q, you need to substitute lower limit, that is 0. So q square, capital Q square dividing by 2 minus 0 is there, so I will left out the whole thing. So I left it out, the whole thing. So what left it then? What is the term we need to move on? So W is equal to, I have the formula 1 by C capital Q square dividing by 2. It is minus 0 is there, so need not worry about this thing. And what is the W1? W is nothing but the amount of work done, right? So this amount of work done is nothing but U. What do you mean by U? U is a U, right? So U means the letter we are using for energy. So U is equal to 1 by 2 Q square divided by C. This is the amount of energy stored in a capacitor. But we have the formula Q is equal to Y is capital V into C. 1 by 2 Q square. Q square means V square into C square dividing by C. C cancels out. What left here? Half C into V square. So this is the energy stored in a capacitor, and here you may use the term for various formulas. You may here use C is equal to Q by V, so form change. You may substitute here V is equal to Q divided by C, substitute it, cancel the term and have the different thing. So this is the energy stored in a capacitor. Well students, for these days we have studied about capacitor and energy stored in a capacitor, and this is how the second chapter ends up. Okay, we'll meet in next session.